In inner-city Cambridge, Massachusetts, Just to Start Corporation, a nonprofit housing development agency, is building 10 units of affordable housing for first-time homebuyers in collaboration with a group of students from YouthBuild. Just to Start is committed to building affordable housing, not just to buy, but also making it affordable to live in. The development represents the first LEED, or Leadership in Energy and Environmental Design, project by Just to Start. LEED is a third-party certification program for the design, construction, and operation of high-performance green buildings. Bruce Harley is Technical Director of Conservation Services Group and an expert on energy-efficient construction.
Energy efficiency isn't usually on people's minds when they buy an apartment or a house, but actually it turns out to be a shock when their energy bills are a lot more than they expect.
Massachusetts weather is both extremely cold and wet in the winter and hot in the summer. This presents considerable challenges in the design and construction of homes. In order to make a home as energy efficient as possible, architects and contractors must minimize three properties in the transfer of heat: conduction, convection, and radiation. These are all properties associated with thermodynamics, the branch of physics concerned with conversion of different forms of energy, and with heat transfer, the movement of heat from warmer objects to cooler objects. We experience this process every day of our lives, but think of it in terms of comfort rather than energy and cost. We will explore one form, conduction, and investigate how it is experienced within the housing industry. Conduction is the transfer and distribution of heat energy from atom to atom, or molecule to molecule, within a substance. Solids usually conduct heat better than gases, and metals better than nonmetals, due to their different molecular properties. All materials conduct heat, even ones that you might not at first think of, such as wood or even wool. All materials used in the construction industry have properties associated with heat transfer, but compromises are always made in the choice of materials.
Wood is not as good at insulating as insulation, but it's not a really good conductor of heat either. So we want to try to minimize the amount of wood that goes from inside to outside, but concrete and steel are much more important. Concrete is more of a conductor than wood, and so we want to make extra effort to try to insulate the concrete between inside and outside. Steel is a complete other order of magnitude beyond wood or concrete. Steel is a very, very good conductor of heat. There's a reason we don't make frying pans out of wood or even concrete. We make them out of steel because they conduct heat from the burner to your food very effectively.
Heat is always in transit from one material to another, never stopped. Heat conduction is the most significant means of heat transfer in building materials. In a building, heat loss, or gain, results from the transfer of heat directly through the materials of what is called the building envelope.
On an atomic level, too small for us to see, conduction occurs as a hot material, meaning rapidly moving or vibrating atoms and molecules, interact with neighboring atoms and molecules, transferring some of their energy or heat to neighboring atoms in another material. Heat is always transferred from warm to cold.
A metal spoon in a cup of hot coffee becomes warmer because heat from the coffee is conducted along the spoon. Plastic is a poor conductor of heat, so plastic spoons do not get so warm. In a similar way, walls conduct heat into a building in the summer, but the same walls will conduct heat from the warm interior to the cold exterior in winter.
When you start out with an uninsulated wall cavity and assume that you're heating the building, it's warm on this side, it's cooler on this side, and so you have conduction through the interior plaster. Once you get some heat flow out into this wall cavity, you're also going to get conduction through the exterior sheathing, between the exterior sheathing and outside.
Dry wood is a relatively poor heat conductor. Steel is an extremely efficient heat conductor. But if we compare these to materials that are far more efficient conductors, such as silver or diamond, it would not seem to be a good idea to build the walls of a house out of diamonds. To minimize energy loss in a building, different forms of insulation are used. The unit used for measuring insulation is R value.
R stands for resistance to heat flow, and there's actually no material that literally stops heat flow. There's always a resistance, so it's slowing it down, slowing it down, slowing it down. And a high R value means it's very good at slowing down heat flow. And so insulation products that we use and the amount that we use typically is in range from, say, R15 or 20 up to maybe R40, R50, or R60 as a very high amount of insulation. If you look at the R value of wood framing in a building, typically that's in the range of, say, 4, 5, 6, 7, when you just look at the amount of wood and the thickness between inside and outside. The R value of concrete, if you look at a sort of an 8 or 10-inch concrete wall, you're talking about R1. So that's sort of almost an order of magnitude less good at insulating. Steel would be the inverse. You can't even measure it in R value. You'd be talking about 0.001 or something like that. So we want to really try to minimize the amount of steel that runs between inside and outside, and where there is that steel, we want to try to insulate it very, very well. And this building is a very good illustration of that, because there's a fair amount of structural steel in this building. So these steel beams are highly conductive, and in the winter, they're just going to be shooting heat right out into the outside world. And so what we want to do is cover them up with a material that's going to stop that heat flow. This staggered stud wall is a great illustration of how to reduce conduction from one side of a wall to the other. In this building, they're actually using these walls in between apartments to reduce the sound transmission from one apartment to the next. Sound transfer is really another form of energy transfer, but it also will reduce conductive heat flow, and I've seen houses built with this type of wall on the exterior. The idea here is, instead of having one wood framing member that runs all the way through the insulation that provides a conductive path, or what we call a thermal bridge, they've actually split up and staggered the studs. One's on one side of the wall, this one's on this side of the wall, and they're going to weave insulation in between them, or they'll spray this with cellulose so that there'd be insulation and almost no pathways that run as solid wood all the way through the wall. So I think everyone can relate to the idea that there's different levels of insulation, and from a very direct point of view, you know, what do you wear when you go outside? You can wear a light t-shirt, you can wear a heavier sweater or a fleece, or you can wear a down jacket, and each of those will have very different levels of insulation. We deal with building materials kind of thinking the same way. Insulation products are designed to be very good at slowing down heat transfer.
Minimizing unwanted heat loss or gain by using insulation and efficient building materials is an effective way of slowing heat transfer through conduction.